400 aircraft lost in 6 months, not to enemy fire, to mechanical failure. The commanding officer calls this acceptable attrition. This was the reality of American aviation in the Pacific War. The solution existed since 1941, but American engineers changed one invisible detail that turned Japanese perfection into a death trap that killed Allied pilots. December 1943. American aeronautical engineer Captain James Mitchell arrives in Brisbane, sent by the Army Air Forces to investigate catastrophic loss rates among newly deployed fighter squadrons. The situation is worse than Washington imagined. Flight logs reveal losses of 25 to 35% from mechanical failure alone before aircraft even engaged the enemy. Squadron Commander Bill Harrison observed, "We're losing more birds to engine seizures than to zeros. Pilots are making emergency landings in the jungle. Some don't come back." General Kenny estimates 30% of all deployed fighters never complete their operational lifespan. In one documented case, a squadron of 120 aircraft receives deployment orders. Only 47 remain combat-ready after 3 months, a 61% loss rate. The maintenance chief considers this normal. The Americans are using engines modified from a revolutionary Japanese design, the Nakajima Homari. Captured intact in 1942, the most powerful radio engine in the Pacific Theater, 18 cylinders, 2,000 horsepower, powers the fastest interceptor in the sky. American engines using improved manufacturing methods are failing constantly. Cylinders seizing, connecting rods shattering, oil pressure dropping to zero mid-flight, pistons welding themselves to cylinder walls. Japanese engines aren't much different in appearance, same displacement, same configuration, nearly identical external dimensions. But they run for 600 hours between overhauls. American copies fail at 150. Mitchell watches mechanics tear down another seized engine. Pilots file reports of mid-air failures requiring emergency bailouts. The entire Pacific Air Campaign hemorrhages the one resource that determines air superiority: reliable flight hours. He sends a cable to right field estimating 40% mechanical losses. Years later, in his 1961 memoir, Engineering Under Fire, Mitchell admitted this figure was deliberately inflated to trigger immediate action. Whether 40%, Kenny's documented 30%, or that specific 61% squadron case, the losses are catastrophic. The Japanese face no such crisis. American pilots capturing intact Japanese fighters find engines that look factory new after months of combat use. These engines become more valuable than intelligence documents. Mechanics study them, engineers request them by serial number. After the capture of Leyte in September 1943, sufficient numbers of intact Nakajima Homari engines were recovered to equip an entire test squadron, who by early 1944 had switched entirely from American copies to refurbished Japanese originals for evaluation purposes. The Nakajima H-45 Homade, Praise, was developed in 1940 by Chief Engineer Nakajima Shigeharu at Nakajima Aircraft Company in Ota, Gunma Prefecture. After competitive trials in 1939 through 1940, a test series of 50 engines was sent to naval air groups for field evaluation. The Imperial Japanese Navy officially adopted it on March 10, 1941, via Directive Kaigun Koku Hambu No. 127. 2 years of testing and refinement before Pearl Harbor. By 1941, Japanese factories had manufactured thousands of these engines in preparation for war. Fighter squadrons were issued detailed maintenance protocols and specialized tools, a tactical advantage supporting their dominance in early Pacific air combat. The design: 18 cylinders arranged in 2 radial rows, each cylinder precisely machined from a single billet of high-grade steel, forged connecting rods with polished bearing surfaces. That manufacturing method would prove crucial. The interior featured hand-lapped piston rings fitted individually to each cylinder. Tolerance specifications measured in 10,000ths of an inch. Oil passages drilled with surgical precision. Every bearing surface mirror-polished. The crankcase wasn't cast, it was forged and machined. The Japanese had specifically required that engines operate at sustained high power for extended periods, which determined the manufacturing intensity. The cylinders featured integral cooling fins machined from solid steel rather than cast separately and welded. One machinist could complete 3 cylinders per day. A strong machinist completed 4. Each cylinder took 8 hours of precision work. The valve train, not standard push rods, but a roller tappet system with hardened steel components. Ball bearings throughout, not bushings. Every rotation point engineered to minimize friction and wear. One engine runs 600 hours smoothly. No sudden failures, no catastrophic seizures, no mid-flight emergencies. An air cooling system designed for tropical operations. The fin geometry and spacing calculated for maximum heat dissipation in high humidity environments. Even sustained combat power in equatorial heat wouldn't overheat the engine. The tight tolerances serve 3 critical engineering purposes. First, compression efficiency. The precision-fitted rings seal perfectly, maximizing power output. Second, thermal management. Uniform cylinder temperatures prevent hotspots that cause seizures. Third, vibration control. Balanced components reduce harmonic stress that shatters parts. The design was classified as a military secret, with its specifications kept from Western intelligence until Allied forces captured examples during the New Guinea campaign. Japanese testing shows minimal failures and exceptional durability. The engine survives sustained combat power, tropical humidity, carrier deck corrosion, coral dust contamination. Reliable, powerful, efficient. In 1942, American intelligence officer Commander Robert Hayes had captured an intact Nakajima fighter during the Battle of Buna. After securing the aircraft, engineers realized they possessed the most advanced radial engine in the Pacific. Japanese technical manuals were recovered from the wreckage, providing complete specifications and manufacturing protocols. Hayes arranged immediate transport to Wright Field in Ohio. American engineers examined the engine with reverence. This was the power plant giving Japanese fighters their performance advantage. The bureaucracy moved quickly this time, too quickly. By spring 1942, samples of the Homade arrived at Wright Aeronautical Corporation in Paterson, New Jersey. The military demanded American production within 6 months. Specifications were distributed to Pratt & Whitney, Wright, and Curtiss-Wright. However, this much is documented. In summer 1942, American engineers began producing their version of the Japanese Homade. American aerospace companies initially embraced them enthusiastically. Revolutionary power-to-weight ratio, superior performance specs, combat-proven reliability in Japanese hands. Manufacturing committees convened immediately. American engineers at Wright Aeronautical in mid-1942 create their version. They retain the displacement, the cylinder count, the external dimensions, the power output specifications. They keep the cooling fin pattern, though slightly simplified. What they change is invisible from outside: the manufacturing process. The Japanese Homare uses precision machined cylinders, each cylinder individually machined from forged steel billets, piston rings hand-lapped to fit, bearing surfaces polished to mirror finish. The tolerances are microscopic, expensive, time-intensive. The American version uses cast cylinders. The cooling fins are cast integrally with the cylinder walls and finish machined. Faster to manufacture, requires less skilled labor, dramatically cheaper. Connecting rods are forged, but not individually polished. Bearings are production standard, not hand-fitted. The U.S. design was slightly lighter than the Japanese engine, 1,870 pounds versus 1,920 pounds for the Japanese version. For engines running at moderate power settings, it works adequately. For sustained combat power in tropical heat, it proves catastrophic. Captain James Mitchell later wrote with the authority of an aeronautical engineer who witnessed the consequences. As any engine designer knows, it is unsafe to run a high-performance radial at combat power with production standard tolerances. The cast cylinder walls, flexing under thermal stress and combustion pressure, develop microscopic cracks. Not gushing oil leaks, seepage. Progressive wear that accelerates under load, a slow, steady degradation that multiplies across thousands of engines. American engineers also simplify the oil scavenging system, reducing the number of return passages. They eliminate the individual cylinder temperature monitoring present in Japanese engines. They use standard ball bearings instead of the premium Japanese equivalents. The cast cylinders are the critical failure. Production begins. Tens of thousands of American-made engines shipped to the Pacific, North Africa training bases. Immediately, universally, they perform worse than Japanese originals. The failures aren't thermatic enough to trigger immediate grounding. An oil pressure fluctuation, a slight vibration at high RPM, a cylinder running hotter than others. Multiply that degradation by hundreds of flight hours. Failures become catastrophic. Not as bad as older radial designs, but far worse than Japanese Hamares. American copies arrive in the Pacific Theater throughout 1943. As Mitchell documents the mechanical crisis, maintenance officers sort engines into categories. Captured Japanese Homares for test flights, American copies for standard operations with reduced time between overhaul limits, older Pratt & Whitney R2800s for everything else. The cast cylinders fail identically to older American engines. Thermal cycling in tropical heat destroys them. Operating temperatures regularly exceed 450 degrees Fahrenheit cylinder head temps. Oil temperatures climb past safe limits. Metal expands and contracts. Cylinder walls crack. Microscopic fractures become visible fractures. Mitchell's December 1943 alarm cable reaches right field. His 40% estimate, admittedly designed to provoke alarm, wasn't far from documented loss rates of 30%, or that specific 61% squadron case. The Army Air Forces finally notices, not because of 1942 warnings, not because of obvious Japanese engineering superiority, because squadrons are losing operational capability to maintenance failures faster than combat losses. Fighters abort missions due to engine trouble. Pilots make emergency landings in hostile territory. In November 1943, a planned bomber raid requires fighter escort of 80 aircraft. Only 52 are mechanically sound enough to fly. The mission is scrapped. Maintenance crews work triple shifts. Supply columns carry double the spare parts because everyone knows engines won't last their rated hours. Squadrons operate at 60% strength because aircraft are perpetually grounded for engine work. The response isn't halting American production. The response is letting the British handle it. British factories in 1944 begin producing faithful copies of the Japanese original under license from captured specifications, precision machined cylinders, full oil scavenging systems, proper bearing tolerances, no manufacturing shortcuts. By mid-1944, 50,000 British-manufactured engines shipped to the Pacific Theater. By early 1945, engines were being manufactured in Australia as well. Hundreds of thousands more follow for the final campaign against Japan. These British engines work, They don't seize. They survive tropical heat and carrier deck salt spray. They run for 600 hours. They deliver rated power consistently. Everything the Japanese original was, now manufactured by the British. American production continues making inferior cast cylinder versions alongside British precision machine versions. A single fighter squadron requires approximately 150 engines annually, accounting for combat losses and scheduled overhauls. The reliable engine shortage would haunt Allied air operations throughout the Pacific Campaign. In August 1944, lack of operational fighters caused by mechanical failures actually limited the air support that could be provided to ground forces, even though replacement aircraft sat on airfields waiting for engine swaps. The island-hopping campaign required consistent air superiority. Squadrons couldn't maintain operational strength. By October 1944, maintenance logs showed engines averaging 180 hours before failure, one-third of Japanese engine longevity. According to official engineering reports, the problem stemmed from inadequate attention to manufacturing tolerances and thermal stress management in adapted foreign designs. By VJ Day in August 1945, over 200,000 engines of various types were required to maintain air operations across the Pacific Theater. Total Allied production of Hanore-derived engines reached approximately 85,000 units of various quality levels. General Hap Arnold observed in July 1945, "Without reliable power plants, air superiority is impossible. We learned this lesson at tremendous cost." The exact number of aircraft lost specifically to American cast-cylinder engines cannot be calculated from surviving records. As Mitchell noted in his 1961 memoir, little about the engine adaptation program appears in the official histories. The procurement offices that rushed production continued minimizing documentation of the engineering failures. What is documented? Severe Allied mechanical loss rates in 1943 through 1944, Japanese engine superiority, British manufacturing of proper precision-machined copies by 1944, eventual Allied reliability improvement in 1945. The Japanese Homare succeeded because Nakajima Shigeharu understood that every detail matters in combat conditions. The precision machining wasn't optional. The hand-lapped piston rings weren't optional. The individual cylinder fitting wasn't excessive luxury. Everything served a purpose, tested under extreme conditions. American engineers kept external specifications and changed internal ones. They assumed cast cylinders would suffice. They assumed simplified manufacturing would be acceptable. They assumed the details didn't matter as much as overall performance specs. They were wrong. While exact statistics remain classified, consequences were measured in pilots bailing out over enemy territory, missions aborted for mechanical failures, and American squadrons requesting capture Japanese engines over domestically produced ones. This is what happens when specifications are copied but not craftsmanship. When cost reduction is prioritized without understanding why every manufacturing decision was made. When good enough is assumed without endurance testing. Post-war military specifications governing radial engine construction eventually mandated precision-machined cylinders and hand-fitted components, effectively abandoning the American mass production approach. The lessons learned influenced every subsequent American aircraft engine program. The Pratt & Whitney R4360 used precision manufacturing. The early jet engines learned from these mistakes. Modern turbofan engines are machined to tolerances the 1942 engineers couldn't imagine. Japan created a masterpiece through necessity and meticulous engineering. America initially botched the copy through cost-cutting and assumptions. The design that prevailed was the one where every detail had a purpose. Engineering details matter. Manufacturing shortcuts have costs. Sometimes the best approach is faithful replication of proven excellence. The Homari story reminds us that invisible engineering choices often matter more than visible specifications, that institutional pressure to cut costs carries real consequences, that in engineering, as in war, details determine outcomes.